Welcome. Now we're going to talk about Green's theorem in the plane. And before we talk about Green's theorem, I think it's important for us to discuss circulation density. So circulation density is different than just circulation. Circulation density is also called either the curl or the K component. So first of all, what is circulation without the word density attached to it? Circulation is the push you get when traveling along a path, essentially a circle. So it's kind of like that speed of traveling along that path, the force that is pushing or, say, pulling you, because it's helpful sometimes when we think about vectors as not just a push, but a pull. A vector field is usually the source of circulation. So if you had a whirlpool, and you stuck a paper boat in your whirlpool. The circulation would be the amount of force that pushes it as it travels in a circle. And the more circulation, say in the center, the more push you have. I almost like to think about it as those things. I know we have one at our aquarium here in the town, but it's like kind of an inverted convex cone, and you drop a coin and it goes in and it zooms around and then it gets down here in the middle and it zooms really fast, that kind of whirlpool shape or idea. So the circulation density is more simply the circulation per unit area. And we could call that the curl, or we call it the K component. It's the rate of rotation, the amount of twisting at a single point. So if you imagine taking this whirlpool idea down and shrinking it smaller and smaller and smaller, and the force is still the same, that smaller whirlpool, you'll have a lot of power in a very small area. And so you will have a large curl. But if you make the whirlpool larger and you're still applying the same force, then you'll have a much smaller curl. And of course, zero circulation would mean zero circulation density or zero curl. So as we said, circulation is the amount of a pushing force along a path, but the circulation density is the amount of pushing, twisting, or turning force when you shrink that path down to just a single point. So suppose we have a flow of water and we want to determine if it has a curl or not. Is there any twisting or pushing force? And in order to do this, we would set this paddle wheel right here into the water, and we would notice if it turns. If the paddle does not turn, that means there is no circulation, and in turn, no circulation density or curl. So what does it mean when the paddle does turn? Well, it means the water is pushing harder on one side than the other, making it twist. And the larger the difference, the more forceful the twist and the bigger the curl. And if this paddle wheel is turning, then it indicates the field is uneven. It's not symmetric. It's not balanced. If the field were even, then it would push on all sides equally and there would be no turn. The fact that there is a twist, that's going to indicate to us that this is not a conservative field. And we've talked about conservative previously. So there's my non-physics teacher explanation of kind of what we're thinking about when we're finding the curl or the circulation density or the K component, which all mean the same thing. So let me pull in our definition. Here, our definition for circulation density for some vector field at a point in the field is this scalar expression. We have partial n respect to x minus partial m respect to y. So again, this is the K component of the curl or just the curl, and we note it as saying curl f dot K. So all these words, if we are trying to find this for a two variable, just x and y function, we'll say partial m with respect to x minus partial m with respect to y. It is important to notice here that if we have a positive curl, that's going to indicate a counterclockwise circulation. Whereas if we calculate this value and we get a negative value less than 0, that would indicate a clockwise rotation. So it would go in the opposite direction. So let's look at some examples and consider some vector fields and try to think about what that visually means when we calculate the curl. In these examples, we're going to find and interpret the circulation density or the curl for each K component. Example A, we've got uniform expansion or compression, and we have this vector field. Notice there's no K, we only have I and J components. So f of xy is cxi plus cyk, and we want to find that K component. So it's important to note, C here just represents a constant value. So we would calculate this and we would say the curl of F dotted with K, that's going to be the partial of N with respect to X, or the partial of this CY with respect to X, which there is no X, so we have 0, minus the partial of M with respect to Y. Again, no Y, so we get 0. And the circulation density is none. That's because this is uniformly expanding or contracting, compressing. We have 0 circulation density because the gas is not circulating at any sort of small scale. Example B, uniform rotation. Here we're given our vector field. Let us calculate the curl of F dotted with K. Again, we'll take Cx partial with respect to X gives us C. Then we have minus Cy, negative Cy partial with respect to Y gives us negative C. So this gives me 2C is my constant circulation density. And this indicates rotation around every point. Again, if that if this curl value is positive, then we would have counterclockwise rotation. If the curl value is negative, we would have clockwise rotation. And I've pulled in this second picture for us, we see something with a constant or a uniform rotation. Example C, our vector field, is just yi. This represents what we can call a shearing flow. And the curl of F dotted with that K component, well, there is no N or J piece here, so that first term would be 0 minus this first partial with respect to Y, we get 1. 0 minus 1 is negative 1. This has a constant and a negative circulation density. If we envision this as that paddle wheel floating in the water and it's undergoing a shearing flow, because it's negative, it's spinning clockwise. And the rate of rotation is the same at each point. And our last example, example D, kind of illustrates the whirlpool effect. So here we have our force field. And if we were to calculate the curl, finding each of those partials, so the J component partial with respect to X, the I or X component partial with respect to Y, using the quotient rule, we get 2 of the exact same expressions, which simplifies to 0. What does that look like? In this situation, the circulation density is 0 at every point except at the origin where it obviously doesn't exist. So that's an idea, or, simply how we would calculate circulation density, or rather the curl. So, again, just thinking about these vector fields, this is a gas flowing in the XY plane, and we were just looking to interpret and think about what the circulation density meant for each of these different situations.